All right, it's 4 o'clock, so let's get started. So, yep, welcome to lecture 20 of CS 545. So because we didn't finish the last part of the last lecture, we'll finish that up and then we'll continue with the real topic for lecture 20, although that one's shorter than a normal lecture, so there should be enough time to cover all the material. So I think last time we left off when we were talking about policy methods. So we spent a lot of time on Monday thinking about here the Markov decision process. How do we find the value for each state where the value is, the expected sum of discounted reward if you have an optimal policy and you play optimally from a given state. But now what we want are policy methods that, given those values, how do you actually get the policy from it? So remember that a policy is something like in this, cartoon here, like it's a specification of what to do at every state. And here, all the states are those grid in the grid world. So again, for most Markov decision processes in the real world, you're not going to be able to enumerate every possible state, but for the sake of teaching, we will use a discrete grid world to convey the concept. Yeah, so remember, we also talked last time about those trees that show the effect of, here's a state represented by the triangle. You go down the tree by picking an action. So you can pick in the case, in the second case here, it's basically picking the action that corresponds to the policy. So pi of state S is the action, basically. And then those circles are going to be the state, the action, but like after we have like committed to that action, but before we have actually resolved it by like executing it and then going to the successor state. And again, today we'll see some more examples of other types of diagrams, but which are a little bit different from this too. And then we also talked about utility for a fixed policy. So a basic operation is compute the utility of a state S under a fixed, generally non-optimal policy, because if you take policies at random, the vast majority are not going to be anywhere near optimal. So, and that's why we have V pi of S here, which represents the expected total discounted reward starting in S and following pi. So whenever you think of values, always imagine like what is the thing that like in the superscript of V. If it's asterisk, then it's the optimal policy. But if it's pi, then it's some other policy. And B pi of S must be less than or equal to B pi of S. Because the value's got to be upper bounded by the optimal one. Yeah. And we also did talk about the recursive Bellman equation from last time that characterizes the relationship between the value for a given state under some policy in terms of that same function, basically, which makes it very tricky to think about because you have like, if one function here equal to something that also has it there. Yeah, so it's a little bit tricky, but the main, at least my intuition here is that it's just a way to characterize a relationship, and if pi is the asterisk, which is the optimal one, then we know that that's basically like the solution that we're trying to get to if we're trying to find some optimal policy. All right, so any question on the review of this before we move on to more policy evaluation details? So I don't have my Google Doc open because like no one has been using it in a while. So I assume people are just comfortable raising their hand. Let me know if you still want that document. Yeah. And just as a clue, like, on like exams, often grid world appears and then you have to analyze it. So just pointing that out to you. Uh, Hi, so let's talk about policy evaluation. We have two policies. So this was like, I think, where we left off last time. One policy is always go right. One policy is always go forward. And evaluation just means, characterize how good each policy is. So for this trivial example, most of you will know what the better policy is, but we can also make it more principled too. So, and again, this is a concrete instantiation of evaluating, you have some policy, you can evaluate like the value at each given state. So, you can see that the numbers might seem reasonable. Like if you get -10, if you're in the lava pit or fire pit, I don't know if it's fire or lava, but whatever. And then you have 100 for the target. I guess it's not shown here, but imagine there's some reward here. Yeah, then you get 100 and 100. The value here is like 70, 48, 33, which it kind of makes sense that for most reasonable values of noise and discount, the further you are from the success state, the lower your value is. Yeah. And it also does make sense that, the numbers here are much smaller, like you have 1 versus 1.09 versus 70.2. Sure, that seems reasonable to me. So let's think a little more about policy evaluation. How do we calculate the values for some fixed policy pi? Just some values for some policy. So again, if we just say policy pi, it's usually not the optimal one because there's an infinite amount of policies that could be there. So one idea is, well, maybe we'll turn the recursive Bellman equation into update. So if you have V0, so if you remember from last time, V0 is like the value that you get when there's no time steps left. But when there's no time step left, you usually get 0 because there's nothing to do. But you can also do this update. So you can do an iterative update, which is like value iteration, which for vk plus 1 pi, this value for this given state is, the value, assuming you have k plus 1 time steps left to do. And it is the sum, it is the weighted sum of the transition probability times the reward plus the gamma vk pi s prime. Yep. So quick review from last time. Do people understand why the gamma is there? Like, do you remember why the gamma is there? That's like an important term. It's the what? The word decays. Why do we do that?
We want to make the right choice earlier, better.
Because we want to make the right choice earlier. Because I think we value the same reward a little more if we get it now than if we were to delay it in the future. Yeah, something like that. Yeah, because this gamma thing is going to come up a lot. This is like value iteration, but it's missing one thing. So you remember that there was a max term, like you had to maximize over the action. Here, we're not actually doing that. Like this thing is just, you have some vector of state, assuming, again, you can enumerate all the states. And then this is an update for each of those states. So the time complexity is O of S squared per iteration. So every time we do one of those arrows, that's the time complexity. All right, hopefully that's clear. No. Yeah. And of course, because we don't have a max, this is like a linear system. It's a little bit more complicated than most linear systems that you can hand draw, but in principle, you could try to do this with some kind of linear system solver. The exact choice is not really of interest to us. Like, it's just that you could do it if you want to. So if we take a step back, we just talked about how do you calculate the values of each state for a given policy, right? So that's like policy evaluation. So hopefully the name is kind of clear. We're just evaluating a policy, right? But this is not actually finding a good policy. We're just evaluating it. Right? So just think about that distinction, which is pretty important. Yeah, policy extraction. So now like we have some value, let's get the policy from it. So imagine you have the optimal value V star of F for all the states that are here. So here are some values. And then I'm just gonna tell you, these are the optimal values, right? Sure, it depends on some choice of, discount, noise factor, and so on. But let's just pretend that those are the optimal values. Like if we have a given state, then how do we get what action to take at that state? Basically, how should we act? What do you think? What does it seem like you should do? So mathematically, yeah, well,
We can calculate the reward of all possible actions and then take the one.
you could try to, you could find the, all right, so I think what you're saying is go through all the possible states, find the reward of going to that state. What if you can't go to some state?
Well, like the next possible, if not possible, but like the next possible.
The next valid possible, the next valid successor state, I should say. All right, so the next valid successor state. I think that's close. So I think what you're saying is a one-time step thing, but you really want to take into account all the possible time steps in the future as well, appropriately discounted. So it's going to be mostly based on the near-term action. So to formalize it, you can pick argmax over all possible actions of this term. Hopefully this term seems familiar because we've already discussed a couple of variants of it. So you take your weighted sum over all possible next state that you could get. And then you get reward plus the discounted sum, the discount times the value of the successor state. The successor state takes into account all the possible future paths from that state. One easier way to think about this is, let's suppose that the transition function is deterministic. So given state an action, you know deterministically what is the next state. Then you don't get a sum because you just get, like, this sum turned out to be like a one term because the t is one for a given s prime and zero for everything else. And then you just argmax over, what is going to give you the best near-term reward plus discount time value of the next state. Yeah. So just to take a moment to just look at that equation because this is pretty important to know. So yeah. So yeah, this is like an implicit way of getting the policy because you need to have some function and then you do argmax. So the fact that you have to do an argmax means it's implicit instead of explicit, which would mean you make this equal to some function directly. Yep. Any questions on that? All right. Next question. What if you have the Q values? How do we act? So you remember from last time when you have in this grid world, there's 4 actions. So that's why you see each grid component has top, down, left, right, and values of that in there. How should we act? Let's suppose that we're in this state here. What's the action? Hopefully you can read the numbers. Or if you're sufficiently back, you can look at the TV back there. Yeah. Or the screen back there. All right, so again, if we're at this state here, what is the best action to take? Up, down, left, right? Left? Go left, right? I mean, when I look at you, you're going right here, but you're going left. Okay. Okay, yeah, you're going left because why do you say that?
Uh, but that direction have the maximum value, so you have the other process.
Okay. Yeah, that seems reasonable. So, right? Yeah, basically. So do you see why it's like this instead of the last time? The last time we just had the value function. Here, if you have the Q value, it's like trivial. So there's a huge difference between this and the stuff on the last slide, even though they give you the same way of giving you the best action to take. The math expression is much simpler here. And that brings us to policy iteration. So last time we talked about value iteration. So value iteration is the iterative algorithm that compute bk plus 1 given bk. So at every time step, you have your value. If you have k time steps left, and then you use that to make your update for the value with k plus 1 time steps left. And then there's a couple of issues. So hopefully, we talked about this earlier. So hopefully it's somewhat clear, like, there's a lot of time complexity. And then 2 and 3 are sort of more efficiency related because when you're doing this, like you might take a max over many different actions, but eventually at some point, the numbers are going to converge. And then the best action is probably going to be, the same one. Yeah, so if you remember from last time, we showed the animation of the grid world, which showed the value changing. And then at some point, like starting at iteration 10, the values were still changing, but the policy was not. The policy was still telling you go up, go left in the same squares. Yeah. So that's what 2 and 3 are basically implying that the policy will often converge long before the values do. So it suggests that there's some sort of like efficiency trade-off. So yeah, this is the same example from last time. We had the grid world value iteration at the beginning, it's 0. Value iteration at the next iteration, it is 1 and -1. Everyone remember what this value was, that k equals 2? We had a discussion about that last time, and there were some conflicting answers from the crowd. And you have this, right, to help. The noise discount and living reward. So remember what this number was?
1.72.
0.72? Are you looking ahead? Oh, cool. Yeah, 0.72. You remember why that's the case, right?
Yeah.
Yeah, so like you get a reward of 1, but it's discounted by 0.9. So it's 0.9, but you also have an 80% chance of going there, and then a 20% chance of going somewhere else with no reward. And so it's 0.9 times 0.8, which is 0.72. Yeah. All right, do you remember what the next numbers were? I don't remember, but
0.85 would be
7, 8. Nope, it was close. But you see why the number increases from 0.72 to 0.78. The fact that the number increases is not surprising, because this takes into account how you could go right and then exit with reward of 1 immediately, which gives you the 0.72. And then last time there was a 20% probability of getting nothing. With 3 times depth left, you could actually get some reward in that remaining 20%. So it increases here. Now you'll see that the numbers at some point are converging. So there's the 0.85 there. But if you look at the arrows are the optimal policy, and it's not changing too much. Yeah. So k equals 12 and k equals 100. So see what happened? Oh, oops. See? I'm going back and forth, and do the arrow change? Nope. Yeah. So sometimes I do that. Like if I want to see if like 2 lines of code are different, sometimes I just go like back and forth on the keyboard and then just see if anything changes. So that's like a tip if you want to like debug or whatever. All right. So policy iteration is an alternative approach for coming up with good policy. So, or at least optimal values, I should say. So step 1 is policy evaluation. Calculate your utility for some fixed policy. Usually not optimal, because when you're starting this, it's going to be a random and very bad policy anyway. And then step 2 is policy improvement, which means you update the policy using a 1-step look ahead with the converged utility as the future value. And then you repeat the steps. So this is policy iteration. So as you might guess from the name, policy iteration is like an alternative approach to value iteration. And the two have different trade-offs. So it can converge a lot faster. No, there's different condition when it might converge. One condition would be, I guess, like if the value still change, but the policy does not, then this thing might, converge a little bit quicker, like depending on how you set, how long your iteration should run and so on. Yeah. So for policy iteration, the evaluation is such that, for a fixed term policy pi, you can find the value with policy evaluation. So this is just formalizing what we talked about last slide. So last slide was this thing with the two steps. This is, evaluation and improvement, which is like, this is basically the formal way to, write out policy iteration, at least a more formal way where, you do this update and then you do a one-step look ahead to find the optimal policy. Yeah. Yeah, so you remember that for value iteration, we didn't have anything like this. Like value iteration did not have like this step. It just had the first step with a max in there. So yeah. So, again, for a comparison and value iteration, each iteration updates both the values and implicitly the policy, because the policy will just be like, a max over the action along with the formula for the Bellman equation. In policy iteration, we alternate between, update utility with a fixed policy, and then we choose a new policy. Yeah, and then you iterate through these two steps. All right, any questions on this? Like there's a big difference between value iteration and policy iteration, but they end up doing the same thing. It's just that, I guess, value iteration seems simpler in theory, but can be slower to converge. And I guess that like it's partly because each path is fast because there's no max, so the time complexity is lower, assuming but then it also depends on like how big your action space is. Yeah. And both of these are, again, types of algorithm. If you've taken an algorithm course, you'll be familiar with dynamic programming, and then that's basically what's going on here. So you want to compute optimal value, so you can use value iteration or policy iteration. If you want to compute value for a particular policy, you use policy evaluation. But if you take those values, then you make them into a policy, you just extract them. So yeah, there's a lot of similar terms. So don't get confused between like evaluation versus extraction here. So, yeah. Yeah, so again, they do look pretty similar, but it gets a little bit easier once you start looking at the differences and thinking about the control flow of how these algorithms work out. All right, so if this were the end of last class, I would summarize, we covered Markov decision processes, we covered value iteration and policy iteration. Coming up on Wednesday, which is, today, we will cover acting under uncertainty, utility theory, value of perfect information, and yeah, following week, we will cover task space regions. So the TAs will release lab 4 like early. They'll release it before lab 3 is due because we have to finish up everything before. I mean, you probably want the lab to be done before your final, right? So yeah, after the final, I don't think any of us want any more additional work. All right, let's take a 5-minute break, and then we'll get to the next topic in today's lecture. All right. Yeah. Usually people leave at the beginning of the break.
Yeah, we just have a small about homework.
Oh, do you have a, what is your comment about the home?
Yeah. But we have some problems, we are trying more than we ever.
Well, yeah, good luck on that. Right. Seems like the attendance is lower, like in-person attendance. Maybe I should stop recording the lecture. Actually, what some classes do is they record, but you need instructor permission to access the video. I think at Berkeley, they, some courses like, or maybe at USC. All right, so maybe we should get back to the class. So now we're going to talk about the main lecture topic for today, which is about like acting under uncertainty and involve things like decision network and value of information. So all this is under the realms of like acting under uncertainty. So hopefully by now you've been convinced that there's many sources of uncertainty. You know, the robot might not have complete knowledge of the state, or if the robot does an action, what is the effect of that? Like that thing is uncertain. So this type of thing is another way to reason about uncertainty and to think about the combination of decisions or action, what an agent should do, variable that could be observed or unobserved, like Bayes net, which in fact you probably recognize the Bayes net here. And then there's the U, which you probably know that it stands for utility. So if you imagine this example, here's an example where the robot could bring the umbrella with it or just leave it at home. And the weather could be sunny or rainy, and then there's a forecast, which is like a noisy version of the weather. And there's 4 different outcomes, right? There's 2 outcomes for umbrella, 2 outcomes for weather, and then there's 4 of these. So hopefully the drawings are clear about what's going on. Like the robot can either not bring the umbrella and it'll be sunny, which it seems like that's the best thing. If it's sunny, but it brings the umbrella, it like bring the umbrella, but it looks dejected because the other robot didn't bring it, and then they're having more fun and stuff like that. Okay, this is just an example of a decision network. And today we're going to talk about MEU. So that's another term, like it stands for maximum expected utility. And the idea here is, can we reason about these decision network and pick, how do we actually pick how do we do this? How do we pick the action which maximizes this expected utility? Like, how do we reason about that? And so you can think of this as a base net, but now you have nodes for utility and action. And the node types are going to be, these are like chance nodes. So those are exactly what you saw in base nets, like those represent random variables. They can take on some value with some probability, and they encode conditional independence assumption. So you can look at a node and then get like a conditional probability table. Now, the difference here is that we're going to consider actions. So those are like the squares. So those are like observed evidence. So it's a little bit different from the normal BaseNet because with BaseNet, you could have like parents and stuff, but here the rectangles are just the action. Like, what does the robot do? So now it's like we're taking BaseNet, but we're introducing action that the robot can do. Yeah, and then the diamond represent utility. They depend on your action and other random variable that the robot does not directly control. So any questions on the setup and the notation? I mean, in principle, you could do something like this with normal BaseNet by treating some of these as, I guess, random variable, but here we're just trying to like sort of formalize it in a different way when we divide up some variables into some that are like action the robot must do, and then some are just values that are like some you can get with some formulas that we'll cover. So yeah, and I guess visually you can tell if it's a bait net if everything is like an oval, and then if it has a rectangle or a diamond, it's a decision network. So bait net versus decision net. So now the point of all this is to figure out how do we pick the action to choose. Yeah, how do we pick the action the robot should execute? And the different steps that are involved, and we'll see some examples of this, are, you would instantiate all the evidence. That means instantiate means you assign a value to that. Yeah. And then you set action nodes each possible way, right? So the action node could be for this action, for all the other actions. And then you calculate the posterior for all the parents of the utility node given the evidence, which means you calculate the probability table, and then you calculate the expected utility for each action, and then you do a max over that. So it sounds like a lot of steps, but you can put it on your cheat sheet, right? And then just read through it and then just apply it. Right? All right, going back to this example. So here's the even simpler example. We don't even have the weather forecast here. We just have umbrella, weather, and the U. So let's suppose that someone just gives you the probability of being sunny is 0.7, and the probability of rain is 0.3. This is actually a reasonable approximation of the weather here, actually. Like 70% is sunny, 30% is raining. But here's something a little bit different. So now we have utility nodes. So before we had the base method, they were only oval. Here we actually have utility. So instead of a conditional probability table, we will have some utility. So the utility of the action of leave. So leave means you leave the umbrella home. If you leave the umbrella home and it's sunny, you get the most amount of utility because you can have fun and don't have to lug around an umbrella. Now, if you leave the umbrella at home, but it rains, then that's the worst possible case. So that corresponds to this case. And then if you take it and it's sunny, well, you're like in this case, then take it and it's raining, you're in this case. So it's not as good as leave sun, but it's apparently better than if you take it and it's sunny. Yeah. Okay, just pretend that someone just gave you these values. So what is the expected utility of the action leave? And by the way, this W here is summing over the different values of the weather, right? Yeah, so take a look at this formula and hopefully just think about what it means. So you have some utility, right? Utility of you leave the umbrella home, and then you have some weather. You weigh it by the probability of the weather, right? So if the weather is always sunny, then you might as well, the expected utility is just going to be the same as like utility of leave and sunny. But here you have to weigh it. You have to weigh the expected utility by the probability of, the variable multiplied by, the corresponding utility if you set the variables at those values. So yeah, just take a quick moment to think about what is the expected utility of taking the umbrella. You can just do the math pretty quickly. Don't do it on your hand. Yeah. Uh, yeah, just want to make sure you're okay. Uh, everyone got the value? 35, right? The optimal decision is leave. Why? 70 versus 35. You just pick the one that maximizes it. Yeah, so it's pretty straightforward. And this symbol here, it means the empty set. So here we assume that there's no evidence. So evidence would mean we know the value of something in the Bayes net. So here we didn't assume any evidence. So it's just maximum expected utility of the empty set. Right. So you can also think of the decision as a tree, like we were talking about Markov decision processes and drawing out the trees of, the state, the action, the next state, and so on. Here, the interesting thing is you can interpret the state, which are the triangles, like how much evidence do we know at some time, right? And so if this triangle is the state, you have different actions you can take. And then depending on the value of the weather, it can take on some other value, and then get your utility. So I think the way to think about this is just do it as another way you can think about the control flow in a decision network. Yeah. So like one path through the tree is like one instantiation of all the variables and actions involved. All right, here's another example. So we have the same, utility. So the utility, the leaving or taking, and then, whether it's sunny or raining, that utility is the same. What is different now is we now have a forecast. So the forecast will tell you that in this case, the weather is bad. So let's just assume that someone gave you this condition, this Bayes rule. So we know the probability of the weather given that the forecast is bad. So you couldn't get that just from, if I didn't tell you that, you wouldn't be able to get that. This is just an example of something that you might get from a Bayes rule. So just imagine that you know this. What's the maximum expected utility in this case? So you remember, I think you remember that the other one here, the maximum expected utility was 70 here, then leaving and taking was 70 and 35. So what are the corresponding values now? Or at least if you don't know what the calculation should be, at least how should the value change? I think that is more important to know, like intuitively, like how should the value change now? But I'll let you think about it for a bit. So, hmm, hmm. At least the maximum expected utility is going to go up or down. The weather forecast is bad. It's going to rain. You think the expected utility is going to go up? That seems strange. That seems strange to me. So let's see if our intuition is right. Like, let's see if the expected utility, the maximum expected utility, should go down. Like, it seems like it should do that, because if you're adding in the evidence that the forecast is bad, then we know that, right? So now we have the expected utility of leading, given that we know the forecast is bad. So in order to get that, you have to do what is the utility of. So again, all this is the expected utility. The way to compute that is you have to do utility of, what your utility table is, multiplied by the weight of that. But this time the weight has to be conditioned on, not just what the weather is, but whether the forecast is good or bad. All right. Does this make sense? Oh, yeah. So umbrella equals leave. So you leave the umbrella at home, you get 34. But it was 70 earlier. Why did it go? Why did it go from 70 to 34? You left the umbrella at home. Well, yeah. Yeah, the probability of raining increases because, because the forecast said it was raining. And usually a forecast is accurate. Although that itself is questionable in some cases. All right, what if you take the umbrella? If you take the umbrella, you get 53. It was 35 earlier. So if you take it, you get 35 last time. Once we know the forecast is bad, the expected utility increased here. So it's 53 now. And the optimal decision now is to take the umbrella. And the maximum expected utility is now 53. Because you just do a max of 53 and 34. Yeah. So do you see why the maximum expected utility went down? Because the forecast was something bad, so the probability should be such that it makes things worse. Right? And if you want to think of it as that outcome tree, so again, just think of this as another way to interpret the themed the themed decision tree. I was about to say Bayes net, and then I corrected myself to the decision tree. Yeah. Decision tree with a Bayes net inside it. That's the right way to interpret. Any questions on the example? Again, just think of this as like, it encodes different control flow, like a single path from the root to some leaf node represents like specific choices of those variables. And if you consider there's another environment that, these slides are based on Berkeley classes, and then they have this Ghostbusters demonstration where, there's a grid where the ghost can be in. And then, there's different sensors that are random variables that tell you, did you sense the ghost there or not? And the ghost location in the Bayes net here is going to point to all of those sensors, and then the action is going to be, do you bust or not? Like this action is like, you pick, if you try to like officially guess that the ghost is there, then you try to catch it. Yeah. And then you get some expected utility. Yeah. So again, this is just another example of a maybe more complicated decision network. And yet this is a larger Bayes net. Like if you want to visualize this, you can look at this video. There's a demonstration by Peter Abeel where he's showing the grid where each cell has some initial probability of where the robot thinks the ghost is. So the robot is trying to like figure out where the ghost is gonna be, and then do the bust action once it sort of has an idea of like where the ghost might be. So I'm gonna speed up the video a bit. Yeah. So what happens is like you do you query like the sensor, then you see that this indicates where the sensor is at, and then it showed that if the ghost is not there, then the updated probability where the ghost should be should like decrease over there, and then it sort of increases in some other areas of the Ghostbusters network. Well, again, they don't. I wouldn't worry about the exact values of this. They depend on a lot of things and like what specific setting they chose for the Ghostbusters demo. Like, I think the bigger point is just understanding how to frame things in a decision network. Yeah, I think that's the bigger point here. So again, just think of it as utility, which depends on action that the robot takes, and a Bayes net that has other variables. All right. So let's talk about the value of information of something. So we talked about, I think if you remember, we talked about the forecast, the weather forecast and the weather, right? And so it seemed like we should be able to compute somehow, like how much estimated or expected value that forecast should be if we're told what it is. And then that's basically what this is saying. Like how many utility points is it worth if we have a decision tree and we're offered to be given the value of some variable. So it's not about making the variable a certain, no, thing. It's not assigning a variable to something. It's just offering to reveal it, which could be, it could be anything, but we're just offering to reveal what it is. So you have to weigh it based on all the possible things that the variable could take on. So that's what we refer to as value of information. So the idea here is, you compute the value of acquiring some evidence. So evidence again is, some value of a variable in the Bayes net. And so the example here is buying oil drilling right. Yeah. I think there might be oil well near here, but just imagine that we have some robot that's like in some place that has a lot of oil, like Saudi Arabia. I don't know. Uh, and then you have some utility, and then there's a random variable, oil location. So that's why it's in the oval. So it's an oil location. It could be in like the first half or the second half. So just imagine we split up the location of where the oil could be into two parts. And the drilling location is the action the robot should take. So should the robot drill in the first or the second place? Yeah, so two blocks A and B each has exactly one has oil, and then the other one doesn't. Then it's worth K utility points. So just some unit, so just imagine it's K something, right? Or K barrel. Yeah, that's the unit for oil, I remember. So the robot can drill in just one location, so it has to pick just one. And then the prior probability for where the robot, might want to drill at would be just 0.5 each. And here are some possible instantiation of the decision network. So again, the main difference here is compared to Bayes net with decision net, you now need utility tables. In addition to some conditional probability tables. So whenever you have U, you should have you should have like something with U at the last column. So what is this showing here, though? It's showing that if you drill it at location A, so the first row is if you drill it at location A and the oil location is actually at A, then you get K utility points or like K barrels or something. If you drill it at location A, but the oil is actually in B, then you get nothing. Same thing if you swap out, if you change the ordering, you get the same thing. So it's like a symmetric example. And the prior probability of where the oil might be is 1/2. Right. So do you see why whether you drill in A or B, the expected utility is K over 2. Is that clear? Yeah. It's K over 2 because if you drill at location A, half the time you'll get K utility points, half the time you get nothing. And so it's K over 2 in expectation. And then the maximum expected utility of what the robot can do is just K over 2 because it's going to get K over 2 no matter like which action it takes in expectation. So here's the question. what is the value of information of O? So the value of knowing which of A or B has oil. Suppose I just tell you, suppose I offer to reveal to you, no, which of A or B has oil. That would be the oil location. If I just offered to tell you that. And I'm literally telling you, where the oil is going to be. So think of the value as the expected gain and the maximum expected utility from this new information. So if you know the oil location, then it seems like you already know where you should drill, right? And then what's the value you get? It's K. So what's the gain? Gain is K. Did anyone catch my mistake? Good. You caught my mistake, my deliberate mistake. It's just a verbal mistake. The slides are correct. I hope they are. So, yeah, the value of perfect information will it determines value of perfect information. So just you'll see that there. So the value of perfect information of knowing where the oil location is K over 2. Because if I'm offering to reveal that to you, your maximum expected utility should go up from K over 2 to K. Yeah. So do you see you kind of see like what the formula might be? Like you take your maximum expected utility with the new thing minus the maximum expected utility without it. And then that's the gain. Can the gain be negative? Think about that. Yeah, it's an interesting question to think about. Yeah. And yeah, I guess you can also interpret it as, you can think of the fair price of information as K over 2 because the fair price is like how much it's worth. And so, if you want K over 2, units of, value, then that's kind of like what you have to pay to get. Any questions about this example? Here's another example. We have the maximum expected utility with no evidence is 70. Do you remember that from a prior slide? Like we computed that value. This is the same utility table that we covered a few slides ago as well. So the same like decision network. The maximum expected utility if the forecast is bad is 53. Again, so those two things we covered earlier in the lecture. The maximum expected utility if the forecast is good is going to be 95. So we didn't compute that, but let's just pretend that I give you that value. So what's the value of information of the forecast? So imagine the robot did not know anything about the weather or the forecast, but I offer to reveal the value of the forecast. So the forecast could be either good or bad. I'm just going to reveal it, whatever it is, to the robot. So there should be some value of information associated with that. But at least, is it gonna be something? Is it gonna be positive? Is it gonna be zero? What do you think it might be? Multiple choice question, negative, zero, or positive. I'm offering to reveal that variable to you, or to the robot. Positive? So here's like an example of what the forecast distribution could be, but the exact distribution doesn't actually matter because you'll see later that it actually has to be at least zero anyway. So it's also very unlikely that it's actually going to be zero because it would be strange if the forecast gave you no value. Because that means the forecast, it has no value, right? So if the forecast distribution is like this, then this formula here, which will give you 0.78, this formula tells you you get a 59% chance that the forecast is good, which means your maximum expected utility is 95. But you also have to weigh it with 41 times the maximum expected utility if the forecast is bad. And then you get this value, right? So there's a general formula here for like how do you compute the value of perfect information. You have this thing at the right. So the reason why the last term makes sense is that you're trying to find like how much value it's giving you in addition to what you already know. So you're just going to subtract the maximum expected utility given what you know like before. And then now you need a value of perfect information if we offer to reveal the variable E prime. And then what is this term doing? It's the maximum expected utility of the set, E along with E prime. So like this extra variable weighted by the probability that the variable equals something. Right? Would that seem clear? So let's suppose that we have some evidence. So we have random variable capital E, and then we're going to assign it some value lowercase. The value if we act now is maximum expected utility of E with this evidence is the maximum over all the possible actions. So now we're generalizing this to consider like any possible action. So generally speaking, the utility is going to be a function of some variable and the action that the robot takes, weighted by the probability of those like assignment to those variables. And then if we see that E prime is, well, at least capital E prime with some other random variable, and it's equal to lowercase e prime, then you get this. Yeah. So I think it's easier if you think of the input to maximum expected utility as some set. So you have a set, it could be the empty set, it could be E, it could be E and E prime, but it's just some set of things that we know. So these are like some generic formulas, and you can also think of S and A as like vectors in generality. Like if you need more things, you could just make them contain more things. Okay? Yeah. So E prime. All right, so here's the thing. E prime is going to be some random variable whose value is unknown, so we don't know what value it's going to take on. And so this is how we compute the maximum expected utility when we reveal E prime. So the way that we can write this in notation is you do capital E prime. So anytime it's a capital letter, it's at least for this lecture, when you have a capital variable, it's like some unassigned thing. And then you have lowercase, which means you assign it. So at least whenever you have lectures that look like they're taken from Berkeley 188, like that's the convention we follow. Yeah. Yeah. And then the value of information is how much the MEU goes up by revealing E prime first, then acting, versus the case of just acting now. And we pretend we don't know what E prime is. Yeah. Yeah. So these are just some general formulas. Any question? Yeah. So, I mean, pictorially, if you want to think of it as the same, like the tree with the triangles as the state, the circles or the ovals as the chance nodes that have the random variables, and then you have the utility that as the diamond, like you can also think of it like that. All right. So some property. It's non-negative. So the value of perfect information for all random variables d prime is greater than or equal to 0. Yeah, so remember I mentioned, I asked you earlier, the VPI is going to be negative, 0, or positive. I mean, it kind of makes sense that if we offer to reveal to you some additional information, then the VPI is like 0. I guess you could always ignore it. And so this is just one of the fundamental properties of this. Yeah. Information is 100% non-negative. It's non-additive, so BPI of EJ and EK of two random variables. It is not generally the case that it is equal to the sum of those individual BPI. So yeah, so if you recall, like let's suppose I offer to reveal to you the variable weather, and then I also offer to reveal to you the variable forecast. Is the value of information going to be, additive? I mean, it feels like some of the information, some of the value that you get from the forecast is kind of given to you if you know like what the weather is and vice versa. So yeah, so you can also think of observing the same variable twice. If you see the same variable twice, seeing at the same time, like right after the other, is not going to give you any additional information. But if you separately sum them up, you're going to like overestimate actually drastically overestimate the value of perfect information. It is order independent as well, so if you do want to, if you do want to like consider an ordering, then you can take BPI of EJ and comma EK. You can make it equal to EJ given E plus BPI of EK, but this time we're now conditioning on EJ. Yeah. So that way, like you condition on it, though, no, that takes care of the case of, if you observe two variables that are exactly the same, you shouldn't sum up the separate BPI. But if you condition on one of them, the BPI of knowing that same variable again, if you already know it is 0. So, yeah. So again, these are just some properties. We're not gonna like actually prove it, but just be aware of the property here. The soup of the day is either clam chowder or split tea. What is split tea? I don't know. But let's just suppose that we wouldn't order either one. What is BPI? So like soup of the day is some random variable. So what is BPI of soup of the day? Can you give me a number or do you need more information? Yeah, just 0, right? I mean, if you know you wouldn't order it, knowing what it is isn't going to change the utility that you get, right? So there are two kinds of plastic forks at a picnic. One kind is slightly sturdier. So what is the value of knowing, you know, which fork you get? So there's a random variable that is in your decision network somewhere that is the fork is equal to something. Yeah. And let's just say that the sturdier fork is better. What is your VPI? 0? Positive? Can you say more? That's probably all you can say, right? Yeah, it's just positive. But you can probably argue that it's just a tiny number because the fork it's a fork, okay? I mean, it's not like you're getting a lot of money, right? It's just something that is very minor. So your BPI is probably going to be positive, but a small number. So you are playing the lottery. The prize will be either $0 or $100. This is a really small lottery. You can play any number between 1 and 100. So it's like you pick a number from 1 to 100. Your chance of winning is 1% because the number that you get for winning the lottery is going to be one of those 100. And so you can pick any value, any of 100 values. And then what is the value of knowing the winning number? So what is BPI of the random variable winning number? 0? Why not? Why not? it's zero, right? I the BPI means it's the value of information if we are offering to tell you what number is the winning number of the lottery. If I offer to tell you that, then your maximum expected utility is probably going to go up because you know the number, then you can pick your action accordingly. Any numbers coming out? Oh, 99? Yep, that seemed reasonable to me, 99. Why not 100? Yeah, so if you don't know, if you have no idea of the random variable winning number, then your expected value is like $1. Because you have 1 in 100 of winning the lottery, then it's 100 times 1 over 100. But if you know what number it is, then the expected utility that you get is, or the maximum expected utility is 100, though it's 100 minus 1, which is 99. Yep, that seems pretty reasonable. Yeah. So what about value of imperfect information? So the way to think about the value of imperfect information is that you might get some random variable that tells you something noisy. So you saw the forecast, right? So the forecast is a noisy version of the weather. So it seems like the information is imperfect somehow. But what will happen in the formulation we consider is that if your data is noisy, that means we just observe some different random variable, which is your noisy version of the original one. And so we always assume that there's going to be value of perfect information. And we use the word perfect, even though the random variables themselves might be noisy. Like forecast is a noisy version of weather, but we'll assume that we take those probabilities into account when we compute the value of perfect information. So if you're wondering why the word perfect is there, it's because we can assume that observe we perfectly observe a noisy random variable, basically. So hopefully that intuition kind of seems reasonable. All right, BPI question. Scouting report. So you're in some place that has a lot of oil, and then you have two places, A and B, that could have some oil. The robot could pick one of those two. And then you're given a scouting report that tells you, well, where does the scout think the oil is located? So think of that as it's like a forecast. It's like a noisy version of the oil location. And you also have a scout who gives you the scouting report. What is the value of perfect information of oil location? So we're assuming the same example from earlier where you had, if the robot picks the right location, right oil location, it gets K utility or K barrel of oil. If it picked the wrong one, it gets 0. And it's 50-50 which one has the real oil. And so the maximum expected utility would be something like K over 2. So what is the VPI of the oil location? Think about it for a bit. All right. Do you think it's K? Do you think it's 0, K/2, or K? Multiple choice question. What is it? 0, K/2, or K? The value of perfect information if you know the oil location. Yeah, I showed it. I just showed it. Yeah. Yeah. But do you see why that's the case? Like I think we covered that earlier. Like it would your maximum expected utility is K/2 if you don't know anything about the oil location. If we tell you what it is, then the robot should just go to the right oil location and it gets K utility. And so K minus K/2 is K/2. Value of perfect information of the scouting report. All right, think about this one. I'll give you a hint. You might have to think about the bathe net here. So I'm offering to tell you what is the scouting report. Here's the scouting report. The scouting report says oil location in A. The scouting report says like oil location in B sometimes. Are you sure it's K/2? Would you bet your life on it? What if the scouting report is noisy? It said oil location in A, but it's actually in B. So with some probability it makes a mistake. Well, it's like the weather forecast. The weather forecast is a noisy version of the weather. Between 0 and K/2. Yeah. So again, this seems reasonable because if you have a scouting report and you don't know anything about like how reliable it is, or you just know that there's a scouting report, then you should get some value, but it's not as much value as if you just got the oil location directly, the ground truth. Value of perfect information of the scout. I'm offering to tell you who the scout is. Maybe it's me. Between 0 and K/2. Why? Take a look at this bathe net. Do you remember this bathe net? Here. Do you remember this bathe net? What are A and B? Are A and B independent? Do you remember what that B structure means?
Conditional.
It's conditional? Here, so we're saying we do not observe C. I'm telling you value of perfect information of just scout. I'm not telling you scouting report. So you do not observe C. You do not observe that. Right? So do you see why the bait net structure implied that? Because the scout and the oil location are independent. So just remember the bait net rule. So yeah. value of perfect information of scout given the scouting report. So now we shade the thing, so it's conditioned on the. It's probably between 0 and k/2. It probably tells you, because it activates the path in the bait net between scout and oil location. So you also, it affects what we know about like what the oil location should be, basically. Yeah. So the general rule is that if the parent um if the parents of U, which are here, are conditionally independent of V, given the current evidence, then the value of perfect information is 0. So if you look at this, value of perfect information of scout given nothing, which means our scout and oil location conditionally independent, conditioned on nothing, which is yes, so by the Bayes-Nash structure. So yeah, that's the Bayes-Nash structure thing. Any questions? You'll probably see a diagram like this in the future. So today we actually covered the part of last lecture that we didn't finish because there was a lot of content there. So we covered the end of Markov decision processes, we covered utility, well, I guess, we covered mostly decision trees and the value of perfect information. So coming up next, I promised to give a lecture on task space region because it's lab 4. So we will try to get it released this weekend, and then you can get a head start on it, and then I'll try to give a lecture on that. And yeah, you can look at how the generative AI was spelling some of the stuff here. Acting under uncertainty. Yep. All right, I'll see you on Monday then.